This problem says if f of x equals 5 plus 3 times x minus 1 to the 2/3 power, show that f of 0 equals f of 2, but f prime of c does not equal 0 for any c in the open boundary 0, 2. And why doesn't this contradict Rolle's theorem? So the first part is simply plugging in 0 and 2 into the function. And as you can see, for both of those values, the value of the function is 8. So now we need to see about the derivative. And here's the derivative. I took the chain rule and applied it here. 2/3 times 3 times x minus 1 to the 2/3 minus 1 is negative 1/3. And the derivative of this inner function x is just 1. So it ends up being 2 over the cube root of x minus 1. Now, is there any value in the open-ended boundary 0, 2 for which this is 0? No. There's actually no value on the real number line where this function is 0. So let alone 0, 2. So there's no value in this function where f prime of x equals 0. So now the question is, why doesn't this contradict Rolle's theorem? Let's look again at what Rolle's theorem states. Rolle's theorem states if these three things are all true, f of x is continuous on the closed boundary a, b, f of x is differentiable on the open-ended boundary a, b, and if f of a equals f of b, then there is at least one value c on the open-ended boundary a, b with f prime of c equal to 0. At least one, if all three of these criteria are met. So let's look at this function and see if all three criteria are met. We know that this third one is met because we checked it. Because if the boundary is 0, 2, and we know that f of 0 equals f of 2, so that one's okay. What about this one, continuous? If you remember what the definition of continuity on a closed boundary is. As for continuity on a closed interval, so formally there are three criteria basically: that the function has to exist for every value, the limit has to exist for every value, and the limit as the function approaches every number in this interval has to equal the value of the function. So there are no holes such as this. This would be a discontinuous function. Informally, you could say continuous function is one that you can draw without lifting your pencil or pen. And looking at this function right here, since the function looks like this, we can basically consider this. We're not dividing by 0 anywhere because this is a positive exponent. So there are no vertical asymptotes where you have to lift up the pencil. So this function is continuous on the interval 0, 2. Now the question is it differentiable? What is the definition of differentiability? A differentiable function is one that doesn't have any breaks or cusps or vertical asymptotes. So the tangent has to be able to be drawn on every point in the open interval a comma b to make it be a differentiable function. These types of things are not okay because there's no tangent line for the function here or here or here. So let's look at the derivative function right here. Look at this. If x equals 1, 1 is in the interval 0, 2. This function has a vertical asymptote. It kind of looks like this at 1. So this is not a differentiable function. Therefore, not all the criteria are met for there to be at least one value c on the open interval 0, 2 with f prime of c equal to 0. So Rolle's theorem is not contradicted because not all of the criteria were met. If you draw this function, it kind of looks like this is 8. Now if x is close to, or if x equals 1, then 1 minus 1 is 0. So this goes away and it's just 5. The thing is, this is a sharp cusp. There is no tangent there. So there's no point on this closed interval where this function has a flat tangent line. This is not where the function has a flat tangent line. All right, this problem says if f of x equals 4 over x, prove there is no number c on the open boundary interval -1 to 4 such that the quantity f of 4 minus f of -1 is equal to f prime of c times 4 minus -1. And then why doesn't this contradict the mean value theorem applied to the closed interval, the bounded interval, -1 to 4? So working on the first part of the problem, proving that there's no c on this open interval, we plug in f of 4, f of -1 and subtract them. We also figure out 4 minus -1. Both of these turn out to be 5, which means we need to find or prove that there is no number on this open interval c such that f prime of c equals -1. So the next thing we need to do is find f prime of c. Find the derivative of that. How do you find the derivative of 4 times x to the -1st? So here it is, a reformulation of f of x is 4x to the -1 using the power rule. F prime of x is -4 over x squared. So if we want to make this equal to 1, doesn't x squared need to equal -1? But if we're working on only the real number line, this is not possible. So there's no value of x that will make -4 over x squared equal to 1. So there's no number definitely on the interval -1 to 4 such that this f prime of x is 1. So this will never happen. So the mean value theorem states that if both of these things are true. If the function is continuous on the closed interval a, b, and if f of x is differentiable on the whole open interval a, b, then there's a number c on the open interval such that this is true. What is this in basic terms? Let's say the function looked like this. Now, because I drew it without lifting my marker and because it's smooth, there are no jumps or asymptotes or cusps. It's differentiable. Let's say that this is the open interval. This is the closed interval I care about. This is A and this is B. So this would be f of B. This would be f of A. This would be B minus A. Then f of B minus f of A over B minus A. That's like the slope of the secant line between the two endpoints, right? In general, informal terms, what the mean value theorem says is that the function is continuous on the closed interval and differentiable on the open interval. There's going to be at least one point where the tangent line has the same slope as the secant line. It might be this point right here. Let's say this was C. You see this tangent line at this point, at this value C? If C has the same slope, if the value of the derivative at this point is the same slope, its tangent is the same slope as the secant line, then if you move this B minus A over here, so that's what the mean value theorem is saying, but it has to be continuous and differentiable. So let's look at this function, 4 over x. Okay? It's obviously not continuous at 0 because 4 divided, but we're talking about the derivative. No, we're talking about the function, I meant to say. Look at this function, 4 over x. It probably looks something like this. And let's say that this was -1 and this was 4. Can you draw this without ever lifting your pencil or pen or marker? You remember the definition of continuity? So, because this function is not continuous on this interval right there, we already know the mean value theorem is not going to guarantee that there is a value such that this is true, because this first one, we don't even have to check to see if it's differentiable. Sometimes you get lucky and you find out the first thing is not met. So that's why the mean value theorem was not contradicted, because its requirements were not met. This problem says determine whether the mean value theorem applies, and if so, find all values C on the open interval AB such that f of B minus f of A equals f prime of C times B minus A, where f of x is 4 plus the square root of x minus 1, and the closed interval of interest is 1, 5. So remember the two criteria of the mean value theorem. What are the two things that have to be true about f of x for the mean value theorem to apply? These are the things we need to check. If f of x is continuous on the closed interval, and if it's differentiable on the open interval. Let's check the continuity. Can you draw this function without raising your pen, or can you say that the limit exists for all values, including the endpoints? And for the endpoints, for 1, does the limit exist from the left? And for 5, does the limit exist from the right? Well, it's a good thing the limit is at 1 on the left, because if it were any further to the left than -1, then this wouldn't exist, would it? But it does exist from the left, because it can be slightly and very less and less, very much as close to 1 but above 1 as possible. And it can be very close to 5 from the left. And you can prove that for every value in this closed interval, the value of the function is the same as the value of the limit. So this function is continuous on this interval. For the differentiability, let's find the derivative and make sure it exists. What's the derivative of 4 plus the square root of x minus 1? Well, this is the same as 4 plus x minus 1 to the 1/2. And if we take the derivative of this, the constant goes away, it just becomes 0. Plus, we can apply the chain rule here, the power rule. 1/2 x minus 1. 1/2 minus 1 is the negative 1/2. And the derivative of x is just 1. So this is the same as 1 over 2 times the square root of x minus 1. So does this derivative exist on the open interval between 1 and 5? Let's say x is 1. That would be bad, because 1 minus 1 is 0, the square root of 0. But we're talking about the open interval, so we never actually get to 1. You know, even right here, this is still a very small number, so this will be a very large value. But on the open interval, this function is differentiable. So since it is continuous on the closed interval and differentiable on the open interval, the mean value theorem applies. So the next part is we want to find all values as it states right there. How would you go about finding what value of C? We can calculate these things. We can calculate this we can calculate this, and we can divide this by this. And let's keep our derivative right here. Because we're going to need that in a moment. But what is f of 5? What is 4 plus? We want to find out the value of f of 5. 5 minus 1 is 4. Square root of 4 is 2. 4 plus 2 is 6. Let's do 1. 1 minus 1 is 0. Square root of 0 is 0. 4 plus 0 is 4. Okay, so f of 5 minus f of 1 is 6 minus 4 is 2 equals f prime of c times b minus a. What is 5 minus 1? It's equal to 4. So we have 2 equals f prime of c for some value of c times 4. You just divide both sides by 4. 2/4 is 1/2. So we're saying that we want to find what values of c make this equal to 1/2. Well, here's the 1/2. What makes this equal to 1? Pretty easy. We make c equal to 2. 2 minus 1 is 1. Square root of 1 is 1. Are there any other values that make this equal to 1/2? No. So this is on the closed interval between 1 and 5. So this is the value. We proved that the mean value theorem applies, and we found the one and only value where the slope of the tangent is equal to the slope of the secant of this interval. And it's at c equals 2.